Topics are from, I think, lecture 21 or 20, 21.
22.
Yeah, I remember, yeah, because I changed it. So that was circular beam stresses, right? So we did not include that on exam 2, so that will be within the scope of exam 3, all the way through the current lecture, axially loaded beams. All right, and homework 10 is due Friday. After today's lecture, you'll have all the information that you need to complete that assignment. Really, it's just the last problem that's related to this lecture. So the others, we've already seen everything we need to know. All right, so do you have any questions for me before we launch into the lecture notes?
Oh, did you decide which project we're doing?
Yeah, it'll be the bicycle crank arm. Mm-hmm.
Trying to figure out if that's good or bad. We'll see.
Guess that'll be determined shortly. I'll present it after we finish up this lecture. And then you can let me know what you think. All right, so as a quick recap, all right, we looked at these axially loaded beams, and the approach that we need to take here is to consider the deflected position of the beam due to transverse loading. Normally we neglect that and say that the change in geometry due to applied loading is negligible as far as it won't affect the statics, etc. But for this scenario, right, if we have a transversely loaded beam also experiencing axial loads, we can't do that because we have to consider the case of buckling. So we make a cut through the beam in the deflected shape position and then applied statics to write our equilibrium equations. And then we defined this term for convenience, right, where little m squared is equal to p over ei. And that leads us to this differential equation for which the solution has a general component and a particular component to it. The particular solution is based on both the transverse load and the axial load, and if there is no transverse load, that particular solution will be equal to 0. So the general solution is only based on the axial load. The transverse load has no effect on it. And then we went through and calculated the constants associated with the solutions to obtain this equation for the total deflection in region 1. So region 1 was defined as the portion of the beam between the left end and the applied transverse load. We would have a similar equation for deflection in region 2. And remember, to obtain those 4 constants, we had to use continuity boundary conditions, right? Where at the location of the deflected load, or at the location of the transverse load, not only is the deflection the same, but the slope is also the same. All right, so we went through that, and then, let's see, yep. So, and then isolated the component of the deflection that's just due to the axial force, all right? So we were able to find that, and then plotting that portion of the deflection that's just due to the axial force against the lowercase delta b, which is defined here as the deflection at midspan only due to the applied transverse force. And this is assuming that the transverse force is applied at midspan. Then that plot will look like this, right? So that's the plot of the solution. We can see that it converges at pi. All right, so Now we're going to consider what happens if we omit the transverse force, right? So remove that from the picture, and we will obtain the differential equation as shown here. So that would give us EI times the second derivative of deflection with respect to x plus axial load P times the deflection is equal to 0. Or we can rewrite that as a second derivative of deflection with respect to x plus the lowercase fancy m squared times deflection is equal to 0. The solution to that differential equation is of the form C1 times cosine of lowercase mx plus C2 times sine of lowercase mx. So this here would be the starting point for any problem that does not have a transverse load. All right, so the boundary conditions that we have, in this case, the beam is simply supported. So at x equals 0, deflection will be 0. That gives us constant C1 of 0. And at x equals L, deflection is 0. So that tells us that C2 times sine of ML is equal to 0. Now, if we conclude that the constant C2 is equal to 0, that would be a trivial solution, right? That leaves us with nothing of any significance. So that means C2 is not equal to 0, which means that sine of ML must be equal to 0. All right, so we're going to take lowercase ml and set that equal to an integer times pi. All right, so n represents positive integers. So we have ml equal to pi, 2 pi, 3 pi, etc. These are eigenvalues for the solution, right? And for n equal to 1, that means ml is equal to pi. M squared times L squared is pi squared. And the critical buckling load is then pi squared times EI over L squared. When n equals 2, ml is 2 pi. M squared L squared is 4 pi squared. And the critical buckling load is 4 pi squared times EI over L squared. Yes. All right, so since C2 is not equal to 0, the full equation for our deflection, and again, this is for the case of no transverse load, is going to be equal to C2 times sine of mx, or in other words, using the information on the previous page that we determined, C2 times sine of n pi x over L. All right, so that's taking ML equal to n pi, or M equal to n pi over L. And this represents eigenvectors. So for n equal to 1, v1 of x is equal to C2 sine of pi x over L. And the deflected shape associated with that would be something like this. All right, where this magnitude is represented by the constant C2. That's the maximum magnitude in that deflected shape. When n is equal to 2, that second eigenvector is, according to the function C2 times sine of 2 pi x over L. And the deflected shape associated with that would be something like this. Not that. All right, where C2 would represent the maximum deflection, which would be even on both sides. So for the purposes of these analyses, right, examining buckling conditions, it's not essential that we know the value of C2, right? So if we go on to another example with a column that is clamped at the base and free at one end, all right, under an axial load, we consider this column can drift, right, under that load, and that would be the buckled shape for the column. So for this scenario, we would take a cut of that column, and I'm gonna sketch here. All right, this distance represents the total deflection at that point. All right, so I'm going to just draw that dashed line, marking the location of the deflection from the original position. And then our free body diagram of the cut would then be something like this. All right, a bit exaggerated here, but this distance then would be delta minus the transverse deflection. All right, so delta represents the total deflection at the free end. And then we have the applied load, P critical there. And at the cut, right, we are exposing internal forces. The only one that we care about is the internal moment, because we're going to sum moments about the cut to find an expression that includes M and P critical. So we would get negative M plus P times the deflection, right, on this. So this distance is the moment arm from P critical to the cut, right? So P times its moment arm, which is delta minus V, has to be equal to 0, right? That's what equilibrium requires. And recall that we have also been defining moment as negative EI times the second derivative of deflection with respect to x. So making that substitution and then also dividing this equation by EI, we obtain the second derivative of deflection with respect to x plus, I'm also going to bring in, let's see, that, right, m squared, lowercase m squared, equal to P over EI that we defined previously. So we can plug that in the second term. So we would have m squared here times V is equal to lowercase m squared times delta. So that's making some substitutions, dividing through by EI, and then redistributing the equation. Now the solution to this problem here will be of the form C1 times cosine of mx plus C2 times sine of mx, and those are all the lowercase m's, plus delta. Now our boundary conditions come from the support at the fixed end. So at x equals 0, we know deflection is equal to 0. So plugging that in, we get 0 is equal to C1 plus delta. So we know C1 is equal to negative delta. And then at x equals 0, we also have a 0 slope. So if we take the first derivative of this expression, plug in 0 for x, and set that equal to 0, we have C2 times cosine of 0 is equal to 0. So that means C2 is equal to 0. So now we have our deflection expression equal to delta times, in parentheses, 1 minus cosine of lowercase mx we still need another piece of information before we can obtain meaningful results. So we're going to make use of the fact that we know at the top of the column, when x is equal to L, this v of x is equal to delta. So that means delta is equal to delta times, in parentheses, 1 minus cosine of lowercase mx, where I'm going to go ahead and substitute L in there, so lowercase ml. So that tells us that lowercase ml is equal to pi over 2, 3 pi over 2, 5 pi over 2, etc. Which means m squared L squared is equal to PL squared over EI. Which is equal to pi squared over 4. So the first critical buckling load in this case is pi squared over 4 times EI. And L squared in the denominator. Somehow I forgot that. Questions? Okay. So the next page is a repeat of this example in a text format, if you want to visit that. Then at the bottom, the main reason I included this page is for the commentary at the bottom. So looking at a few other buckling configurations for columns, right? You could have a clamped end and then a roller end, right? Calling it pinned clamped. And so here you would have the condition of deflection at x equals L is 0. And then your boundary conditions would be the same as before, right? Deflection at slope 0 at the base. You would end up with a critical buckling load of 2.046 pi squared EI over L squared. So a much higher force required to cause this to buckle compared to the free end. And if it's clamped at both ends but free to displace vertically on one end or axially on one end, then you have the same boundary conditions as before, plus you also have slope, the condition of slope at the applied load end is equal to 0. So that increases your buckling load even further, right? And then if we have columns that have axial loads in tension, we don't have to think about buckling. Instead, the deflection of the column or beam due to any transverse load would decrease due to an applied load and tension, as you can imagine, right? So the next page, let's see. Oh, never mind, not the next page. The next page is just a text version of this lecture. Right? Or a summary, I guess, of the lecture in text. The page after that is a discussion on axially loaded beams where you have a transverse load and then the axial load is tension. So again, don't have to think about buckling in this case because the axial load is acting to decrease the deflection caused by transverse loading. So in this case, the deflected shape becomes more hyperbolic, right? So it's a hyperbolic function, and you can see that the deflection ratio, which is what's plotted here, it decreases with the increased magnitude of axial tension. So the note down here says that when ML is equal to 10, the transverse deflection is reduced to less than 10% of what it would have been without having that axial load and tension. So generally speaking, axial loads and tension help us out if we have a beam or a column that's experiencing that. All right, any questions? All right, well then, as promised, final project, posted it on D2L, so it should be accessible to everyone now. This is going to be, and I explained this to the folks that were here last class. Historically in this class, I've alternated between two different final projects. So this is the one that I assigned the first time I taught this class in 2018. And the main reason I assigned this project instead of the one that had been historically assigned to this class that was developed by the previous professor who taught it is because it was the first time I taught this class and I didn't get through the material as quickly as I do now. So I wasn't able to cover the last few lectures that are essential for the other project. So I developed this project instead, which is tied to earlier lectures. But I like how it turned out. I think it's a great project, and so I've been, since then, alternating between the two. So you guys lucked out with the bicycle crank arm this year, and basically we're going to make a lot of simplifications, all right? But the idea is you're going to design and analyze a bicycle crank arm. So you got to consider, right, all the different angles of loading. We've got the schematics shown here, right? So assuming that the load is constantly vertical downwards applied to the pedal, right, then you're going to consider different angles of the crank arm position, right? So basically from this scenario, right, and then you're going to have this scenario and this scenario are the kind of 3 points that would have extreme considerations for internal axial shear moment, etc. But you're going to be considering 15-degree intervals between 90 and negative 90, right? So consider that to be positive 90 and that position to be negative 90. And then this is 0-degree position. So this is going to generate a lot of different internal forces, right? You're going to have to consider the axial force in the x direction, where the x direction is always going to be along the axis, right? So here, that would be x, here, that would be x, right? So it depends on the position of the crank arm. Your orientation of the axes will move with the crank arm. So you consider the axial force, the shear force in y, bending moment about z, right? So this is going to cause, of course, a moment about z. You're assuming that it's fixed to the gear system over here. You're also going to have bending moment about y due to the fact that this applied load is off-center, right? And a torque T.
I have a question about the bending moment about y. It looks like it's a bending moment about x, but maybe I'm not seeing it right.
So the moment about x will be the torque. Yep, so you're correct. You're going to have moment about all 3 axes. Yep.
Okay.
Yep, so you're going to have moment about torque, moment about z. The moment about y is less obvious in this position, right? But you're going to have, like if you think about this position, right, it's a little bit more obvious because your y will be, it'll be like something like that.
Okay.
Oh, that's not quite, that's a little, right, it would be, in this case, how did I draw it? Yeah, so this would be like your z, and then you'd have y. So we're going to consider, again, the forces at 15-degree intervals between those positions. And through that, you will identify what is the critical angle using the effective stress of distortion. All right, so von Mises criteria will be applied. And on the next page, I've got a cross-section sketched here. So these are the 3 points along the cross-section that you'll consider for calculating stresses. So that's what that line is pointing to there. All right, so now this is where the analysis and design is going to be a little bit separated. So you're going to consider 2 different cross-sections, a solid rectangular section and then a thin-walled rectangular section. First, the solid rectangular section will be used to conduct the complete analysis that shows that the section is adequate, right? And for that, I give you all of the dimensions that you need. Well, the crank arm dimensions don't change, right? The cross-section dimensions are shown here. So when you switch to the thin-walled rectangular section, these dimensions will still apply. They're just going to represent the outside dimensions. So your task is going to be to determine the minimum thickness that will be required for the walls of the thin rectangular tube. All right, so verify that the solid section is adequate, then consider a thin-walled rectangular section and find the minimum thickness for the same outside dimensions, material, and loading. For the thin-walled section, you also need to consider the potential for buckling. So that's why I mentioned that today's lecture would be relevant to your project. That's going to be a check that you do after determining a final thickness, all right? And if everything was done correctly, you shouldn't have a problem with buckling, right? So it's just a check that you're going to make. And then in all cases, we're neglecting stress concentration, so you don't have to worry about the corners and things like that. Now, the loading is given here. You're going to just assume that the applied vertical load is 225 pounds and doesn't change. So again, right, realistically, the loading will vary, but we're going to assume that the expected loading will not exceed that value. So that's your design target. And then we already talked about that a bit. So you've got your dimensions for the crank arm, and then cross-section and material properties shown here. So the procedure is outlined here, and I'd like everyone to follow this and present those tasks in order as much as possible in your report. So we'll go over that in a little bit as well, what the report requirements are, So first, I want you to draw 3 complete free body diagrams, one for each of these 3 positions, right? And include in those free body diagrams values for each internal force that applies, right? So not all of those internal forces noted here are going to be present in all 3 of these positions, right? So some positions will have certain things but not others, and so on. And when you do this, I'd like to see it in terms of P and theta, right? So that's not the point to plug in a value for P. Just draw free body diagrams and write the equations or the expressions for internal forces in terms of P and theta. And then that's going to set you up, right, for understanding what you need to tackle the rest of the project. So for each location then, on the cross-section, those 3 points, I want you to calculate the stresses at 15-degree intervals of the crank arm position and identify the critical angle by evaluating the effective stress of distortion. For this portion, you're welcome to use Excel or MATLAB. Just make sure that you provide, clearly documented work. And let's see, it says when calculating shear stress due to torsion, use the approximate methods discussed in class. So for the solid section, that would be using that table that has the K1 and K2 values, right? And for the hollow section, that would be applying the thin closed tube, thin-walled closed tube section, right? All right, so then here I say each individual is assigned an angle for which you are to provide a full set of hand calculations for step 3 for points A, B, and C. Those angle assignments are on the last page of the document. For point B at your assigned angle, I'm asking you to draw a Moore's circle and identify the principal stresses at the maximum shear stress and the maximum shear stress, right? For this, just treat it as a solid cross-section. All right, so we're still in solid cross-section land. And then figure out what is the orientation of the principal stress state. Now, in step 6, you're going to move on and consider the thin-walled section. So here, you're going to use the von Mises criterion and determine the minimum required thickness. I'm also noting that you can go ahead and assume that the critical angle, the orientation of the crank arm that is, will be the same as it was for the solid cross-section. In reality, it should be the same within about 5 degrees, so that's a good enough approximation. And then you'll check that section against buckling. For that, this is the position that's going to be susceptible to buckling, right? Most susceptible. So that would be what you use for the buckling check, and you're just going to show that this is the solution to the equation, and then solve for the critical buckling load using the analytical method that was presented in lecture today. Here I say if the section needs to be redesigned, calculate a new minimum thickness. And again, if you calculated everything correctly, you shouldn't need to calculate a new minimum thickness. So that should just be used partly as a check to see if things worked out the way it should. All right, so questions so far? Okay. All right, so the report it should be typed, except for the required hand calcs. First part will focus on an overview and summary. So it doesn't need to be very long, just provide a brief summary of the problem statement, your results, and discussion, right, about the forces and conditions that drive the design. Then you'll have your free body diagrams and initial analysis. So this will include your hand calculations. And then presenting the complete analysis results and your final design. So I describe this through here, right? Make sure that you include some tables that list the stresses due to each internal force for each arm angle. Provide a plot of the effective distortion stress versus crank arm angle. Identify the critical angle and the location on the cross section, right? Which point is most